Hi, welcome to Cloud Cover. My name is Ryan Dunn.
And I'm Steve Marks.
Great show today. We're going to be talking about building your own very huge distributed computing MapReduce high compute scenario in Windows Azure. Additionally, we will cover the news as always and have some tips on how to minimize downtime and maximize the visibility of your virtual IP address in Windows Azure.
Let's start with some news. We probably should have said something about this in last week's episode, but there's a new version of the Windows Azure Platform Training Kit, cleverly called the June update. Don't know where they came up with that title, but that's what's there. What's new in this, Ryan? Do you know if there's some fantastic new things?
So a lot of the hands-on labs have been updated to latest SDK releases, as well as Visual Studio 2010 in some cases. I believe a few of the presentations as well have been updated. So in general, it's just cleaning
There's
up some
one,
of the
right?
stuff.
Is this new? Is this actually new? This
Yep,
is
new exercise there.
working with drives, which is cool. So if you wanted to figure out how to do that, SSL in Windows Azure, which we talked about last week on the show.
Correct.
Which is yet another reason we probably should have mentioned the June update of the Windows Azure Platform Training Kit. But anyway.
Well, it's
better
just
late than never.
it's just so popular. It's kind of like announcing, hey, the sun's coming up today.
Yeah.
Almost.
It's a good point. In other news, the sun is coming up today. It actually already did, but it'll come up tomorrow also. No, let's actually move on. Cloud Cache.
I ran across Cloud Cache as I was perusing Codeplex the other day, and actually this looks like a really cool sample, not only in the amount of effort that this coder has gone to, but additionally it covers a scenario a lot of folks ask about, which is how do I get distributed cache up and running, and specifically memcached.
Yep.
And what this is it's a dashboard as well as a framework for essentially deploying memcached. And if you take a look kind of at the screenshot there, you see the dashboard itself tells you how many reported instances you have, as well as like the transaction rate, the hits that you're getting, and allows you to kind of control the cache. You can flush it, you can do different things. So it's pretty comprehensive. I thought it was a great thing. Now, I have to caveat it saying I haven't tried it yet. I'm just going by what I see here and what is in the description. So it looks really cool, and I thought it'd be worthy to kind of point out.
I like that it was released on April 1st.
Yeah.
Despite knowing that everyone's going to think this is an April Fool's joke. So everyone did it. I guess it would be a sort of lame April Fool's joke. Hey, here's some useful project. Just kidding. I don't know.
Hey, geeks might find it funny.
So maybe people knew. But yeah, this is cool. So there's also the memcached solution accelerator.
Correct.
That if you go to windowsazure.com/interop, I believe, you'll find that thing. And I believe this is sort of loosely based on that, in that it does sort of the same thing to get memcached running, but it has all this stuff on top of it to kind of keep track of things and report back and whatever. So it's got a whole other layer.
It also uses a slightly different client library.
Does?
I think the client library that's in the solution accelerator has been optimized for ASP.NET cache and session state and stuff. This particular client provider, I don't know that it has that, but I don't know that it doesn't either. I just know it's a different client.
Oh, okay. Okay. Well, someone should check this out, and then they should tell us on Twitter.
Yeah.
At Cloud Cover Show. See how I just slipped that in, in conversation. They should tell us what it's like and how it went.
Yeah, I know a lot of people asking about it, which is part of the reason I'm bringing it up.
Yeah. Enzo SQL Shard.
Yep. So this whole thing about the cloudiness of the world is that we want to store lots and lots of data, usually because we want big, huge, scalable services. And part of that is you need to partition your data. And partitioning can either be a logical operation, kind of in the Windows Azure table storage world, where we have partition key exposed, but the partition doesn't necessarily have to be on a different machine. It could be on the same machine, and logically it's a different partition, however. Or in the case of SQL Azure, you actually, when you shard, you create a different database, which we do put on a different machine, which gives you parallelization of resources. However, what that means, though, is that you need to now fan your queries and aggregate results. To do this, there's a few ways you can do it, obviously. One is kind of code it yourself. Use some mutexes, use some synchronization primitives, and kind of do it yourself. Or you could use something like the parallel task library or PFX And the other is use something like a framework that someone else has built. Now, this was this was actually put out. I noticed it in the Twitter stream for the SQL, from the SQL Azure team the other day. Again, I haven't tried this because it's pretty new. It's just released a few days ago. Well, more than a few days ago, apparently.
Yeah. But hey,
it is a sharding library for SQL Azure. So it does those things that we're talking about, which is fan those queries and then aggregate the results back. It also implements some things like caching. Now you notice it is using the TPL in here, the test parallel library, which, as I said, is something that you can clearly do yourself as well.
Very cool. And this is horizontal partitioning, I noticed, which is just generally useful to know the difference between horizontal partitioning and vertical partitioning. And horizontal partitioning is
like this.
Slice it this way, which
means it's like level to the ground.
Exactly, with the horizon.
Yeah.
Actually, I think that might be where the word comes from, which means different rows are on different servers. Right? Vertical partitioning is sort of the other option, and hey, it goes like this, in line with the Verizon.
Yeah,
Verizon. With Verizon towers, if you've seen the cell towers, that's where actually the word vertical comes from. And that means different columns are on different things. And you actually need sort of a different strategy for if you're splitting vertically, then the issue is sort of which columns do I actually need back from this thing. And if you're splitting horizontally, it's which rows do I need and what servers are those on. Or fan it out to all of them, sort of aggregate the results, which it looks like this really makes easy.
Yeah. I like to think of horizontal as the tables are all the same, just the data varies, and vertical as the tables are actually different. They're different data stored differently. I should also note that we do have some sharding guidance and samples in that June update as well. If you go look at the SQL Azure samples we have in there, we actually have an entity framework provider that has partitioning strategies and also does this sharding behavior for you.
Cool.
So you specify, I'm going to partition by whatever your column is, and it will do the right thing and set it to different databases and fan the queries and aggregate as well. So, people have been thinking about this, and I think over time this will become more and more natural behavior for SQL Azure users.
Great. All right, one last piece of news, and then we'll move on to the feature. This is about affinity groups. So this is a blog post by Monte, who is on the Windows Azure team and works on the portal and some other sort of front-end kind of things in the developer experience. And he's got a blog post that answers a question that we get somewhat frequently, that is just what are those affinity groups? So for those who haven't done it, if you go to the Windows Azure portal and deploy something, you have an option of where to put that, so what region and sub-region. So for example, South Central US is a specific sub-region, and you can deploy it there. You also have an option of creating an affinity group, and then you can put multiple services or a service and its storage account, or multiple services and multiple storage accounts, whatever you want, into that affinity group. And that affinity group also has a location, and then everything goes there. And people have often asked, is there a difference between just putting everything in the same subregion versus putting them in the same affinity group? What does that do?
Right.
One actual nice thing that shouldn't be ignored, and isn't really in here, but one nice thing about using it in an affinity group is that you can't actually make a mistake. We've actually had customers who said that as compared to sort of other cloud platforms they were looking at, they really liked Affinity Group because they didn't make the sort of mistake where somebody just clicked the wrong subregion and deployed somewhere else, and now you've got all this traffic going across the country or around the world potentially, when you really wanted those things to be close. And in that, so Affinity Group just protects you from that. So on the surface, it's just it's easy for that. The reason you want everything to be together is generally to lower your latency and to get the free bandwidth, which we give you if all these services and storage accounts are within the same subregion, then the bandwidth is free. And that can make a huge difference depending on sort of how chatty of a protocol you have with different components. So that's a really big deal. Affinity groups are one way to do that, but actually as long as you put everything in the same subregion, you get that much. The thing that Monte talks about here is that Affinity Group can actually go further in that we make an attempt to actually put those services or those storage accounts sort of logically close in the data center, I guess is probably the best way to say it, like as close as possible in the networking sense, so that you get the lowest possible latency. And so we actually make an attempt to do better than just if you just said the same subregion. We'll try to get the same corner of the data center so that things are actually really fast. So it is a best practice to use affinity groups to get that. There aren't any strict guarantees about what you'll get when you do affinity group that way, but that's sort of your signal to us that you care about these things working together and having very low latency.
Right.
So there's more in here, but Tony basically put together a post that answers these kind of questions. So check that out. With that, I think it's about time we move on to our feature of this week, which is how to run basically big kind of scale out computation processes in Windows Azure. And I thought to demonstrate that, Ryan and I should just each take half of what we want to explain and just at the same time explain it into the camera.
That way we can scale out.
That would be much faster than if we do it serially by me explaining something and then Ryan explaining something.
Okay, so ready?
So, all right, ready. 1,
Okay.
2,
So the first
three.
thing you have to keep in mind
you have to make sure that after you've gotten all the results,
it's not going to work. We keep running over
It's
each other.
hard. Okay.
So we actually need to coordinate.
Yeah. So maybe we should talk about how you do that. That was like one of the lamest things that we've done on the show, I think.
No, we could beat that.
Okay.
Trust me, we could take that one.
Let's show some pretty graphs because everybody likes that.
Yep.
So we have a sample here which you can get too. Where is that? You can get that over here. It's called the full Monte
That is correct.
because it's a Monte Carlo simulation.
And it bears all in the world of Monte Carlos.
All of the source code is available for you to read.
That is correct.
So this full Monte sample is here, code.msdn.com/fullmonte, and we'll put a link for that later. Let's show what it does
Sure, and then
and
let's
the magic of it, and then we'll talk about how it's put together and some sort of general advice for how to build things like this yourself. All right, so what am I supposed to do? Can I hit start now?
Well, let's first explain, right? This is an Excel client.
I want to hit start because then there's a graph already.
Okay, go
I
ahead.
like graphs.
Go ahead
I'm pressing
and
start. Now go ahead.
So there's an Excel
We're
client.
parallelizing.
And the Excel client actually is submitting a Monte Carlo simulation to the cloud to be computed. So, you can run these in Excel, but if you want to do lots and lots and lots of iterations, obviously you need bigger and bigger hardware. Or you could just farm it out to the cloud and say, you do the simulation for me and send me the results when we're done. So we did that. Essentially what we have is a pool of worker roles that are listening for jobs coming in, and the job is a particular Monte Carlo run, as defined by the parameters at the top of the screen. So the number of runs, the periods, etc., the up and down, open and interest, and those kind of things. Once you submit that job, it gets picked up by a role, and then it starts working. It breaks apart the actual job itself, and we'll go into more detail on how this is working. But it breaks apart the work that we need to do for the simulation, assigns it out to the number of roles you have assigned, and then starts computing the results. Right. What we see right here is that we have one role working, and it's doing what looks like 12,000 messages, 1,200 messages. And you can see that we're kind of calculating the remaining time to be around an hour, and 2 minutes have gone by so far.
Yep.
Right, so this thing is running, and you'll see that over time you'll kind of average out to about 1,000 runs a second. Well, we want to boost this up, so go ahead and knock it up a few there, Steve.
All right, let's kick it up. So now it should be 5 as these things come online. There's a little bit of delay as these.
We have to go tell these roles to
start.
wake up and say, hey, there's some work for you to do now.
Yep.
And you'll see it right away that the stuff starts jumping up. We start getting almost linear increase here, and you'll see that the amount of time that we're scheduled to be working has been dropping as well. So from an hour down to 15 minutes, and et cetera. And finally, we're doing, how many runs are we doing here? 8 million, and we got 7.5 remaining.
Yeah, this we don't have enough time in
we
this
don't have
show
enough time,
to really
so,
wait the
so
12 minutes
go big bang.
left. So here we go.
Bang!
Bang! Kick it up a notch.
Yep. We're taking
A
all
lot of
the,
notches.
we're gonna
So
we're gonna jump them all.
Everything. We'll take everything that we have, which is what's the total number? It's like 68. I think
68
we have
total.
68 VMs in the cloud, so role instances in the cloud that are working on this. Now they're all doing it at once, and hey, it's only going to take a minute now. We're halfway done.
Yep. And this thing just flies, right? It's computing all these calculations and it's sending it back. We're actually using the service bus to send it back. So when this Excel client started up, it registered itself on the service bus and said, "Hi, I'm listening," and the worker roles are firing all the results at that endpoint. and then we're capturing it here and graphing it out, and
So that's what
showing
this
you.
graph is, right? So actually, if we move down, this is where we started. You can barely see it anymore, what it looked like when it was just one sort of moving along here. And now you just saw it drop off because we just hit 0, so we actually finally finished. This is sort of the peak throughput that we got.
Yep.
Very cool. So it took total 3 minutes because really we wasted a little bit of time. Then we put on the max and it finished it really quickly. This estimated cost was here. We didn't really talk about it, but it's sort of estimating based on VM usage and how much would this cost to do.
How much
And
of this particular slice of work did that actually cost you?
It actually went down a little bit over time. My expectation would be that it would be the same because I'd have one instance running for n hours, or I'd have n instances for 1 hour, and those numbers should come out the same. Do you know why it actually looked like it went down?
It actually goes down because it turns out that the more instances you throw at the problem for the shorter period of time, there is a tipping point where the instances are faster than the billing period you have, and so essentially you're getting some benefit to throw more at it. So if you were to let a single hour go for, or a single instance go for an hour, I mean, you think about it this way: if a single instance went for an hour, you're gonna pay 12 cents, right? And if you can get a whole bunch of instances doing it really fast, you're paying for the fraction of it across all those instances, in which case you're coming out ahead. So that's really what it's doing. Now, obviously, this is great, is a great model if you're sharing this resource with lots of other workers and everything as well. Now, if you're just throwing 70 VMs up there to do this
for a minute,
to do this one spreadsheet for a minute, probably not economically viable, but you get the idea. The point here is you can have these pools of resources up there, submit jobs to them, and they do a map reduce operation to actually return the results.
Right. So you can imagine that, at the company Ryan and I founded, do awesome stuff incorporated, that we would have 70 VMs up in the cloud working night and day on a whole bunch of stuff, and different employees at the company might go fire up, allocate for a while, and this actually handles all of that of kind of, we didn't really show that part, but the first step was really me allocating how many of these instances I was going to use, and so I take those ones over, submit my job, use it for a few minutes, and then give it back to the pool. And there you get really nice economic characteristics about kind of spreading out the costs and making sure you get full utilization out of everything the whole time. So this is cool, and you can check out all the code. There's a lot in there because there's also that service bus reporting back. There's a bunch of queue stuff. There's some WCF services. It's a little bit daunting when you open it up, but that's because there's actually a lot of interesting stuff in here.
But there's really only 3 key components to this. One is the computation unit itself, right? The thing that actually calculates the results, right? There's a scheduling service, and then there's a registration worker. Those things all together really pull this together. And the characteristics that we want to talk about for this show is really on kind of the bigger problem of what we're trying to solve here. And I think we should probably, we can couch it in terms of a little bit of full Monte, but I think we'll go even more general than that.
Let's talk about it in general. I mean, the first thing we talk about is breaking up the work. So in this example, I'm going to close this because it's already because it's flashing all the time. It's distracting me. I'm going to close this. But in this example, we had basically 8 million runs. I think was the total number. 8 million runs that actually had to be done. And so breaking up the work is the nice thing about a Monte Carlo simulation is that those runs can be done independently, right?
But we can show this. We can actually show this kind of on the board as well, and kind of think about different ways that we can build it. But at the end of you were starting to say before I rudely interrupted you to tell you to go to the board is we have a whole bunch of units and we have a whole bunch of work. So the question here is how do you efficiently allocate the bunch of work that you have to the units? And there's a trade-off, right? There's coarseness versus granularity. And I think that's what we're going to be talking about here.
Yeah, so let's say there's a giant piece of work here. Up in the cloud, we have a bunch of, it's confusing that I'm using boxes for both servers and work, but hey. So these are the VMs, or the workers that are actually capable of doing this. If we just have this big chunk of work, the best thing that we could do is just send it to one of these VMs and can operate on it. And obviously not efficient, doesn't make use of kind of the scale out model. And so we want to break this up into pieces. And so there's often this step that's maybe partition is a word for it. I'm just going to say, like break up, which breaks up the work, which basically takes this into small pieces. And what Ryan was just saying is, that's really important is you have to decide. First of all, you have to have a way to do that. You have to have the kind of work that you can break into pieces. And in the Monte Carlo simulation, it's really simple because each one of those runs is completely independent of the other ones. For different kind of tasks, you have to give some thought to that. So the most important characteristic is that you have work that can be split up. And so you might have some code that breaks this into a bunch of smaller boxes. Then you have to think about how big those boxes should be. So in the Monte Carlo simulation, the smallest boxes we can make, there would be 8 million of them for the example run we were just doing, because there are 8 million independent runs. We can't go smaller than that because the actual run depends on itself, and so you need sort of locality of that. You have to do all that, the entire run itself. But you could have 8 million pieces. 8 million is a lot, and there's actually reason to not want to use 8 million. So there's actually a trade-off between...
The flip side, though, you could go the other way, which is you divide it exactly evenly by the number of VMs you have.
Right. So one thing you can do, so to keep, the first example was, look, if you had this big chunk of work, only one VM could do it. To make sure that all the VMs can operate on it, you need at least that many pieces, right? Because then they can each get one piece. That's sort of the bare minimum of how much slicing you want to do. And then, right, as you go the whole way to 8 million pieces, you run into a different problem, which is that it may actually take more overhead of just passing the messages along and distributing the work. If, for example, you're reading a queue message for each one of these 8 million pieces of work, the work itself may take a few milliseconds, but reading the queue, unpacking the message, and whatever might take a lot more time than that. It might take a bunch of bandwidth. And so you don't want to go to that extreme. And so the question is, what's the sweet spot for your application between one big piece of work and a whole bunch of tiny pieces of work? And Ryan was saying that when the full Monte sample was being developed, that the sweet spot ended up being about, what was it? It was like 2 to 2.5.
Yeah,
I think.
I'd have to go look again, but we tried. I mean, we tried both scales. Like we initially tried 8 million messages. I mean, saying, hey, why not? That would be the most scalable solution. Like in a world of zero friction, no I/O overhead, no overhead at all for passing messages. You put 8 million messages into a queue, and then you don't care how many instances you have. Every single one of those pieces of work is idempotent. Everything works perfectly, right? That's in theory. Yep. In practice, the overhead of just inserting messages, 8 million messages into a queue, dequeuing 8 million messages, doing the calculation, and then passing the result back for aggregation was so much higher than the work that actually was done that it was a complete non-starter.
Right.
So we then said, okay, what if we did the opposite? Let's just break up the work exactly by the number of VMs. We know at time when you allocate how many you're going to have. So when you submit a job, let's do exactly the amount of work divided by the number of VMs.
Yep.
And that works for the most part. However, that has problems as well. The problem there is if you have a shifting pool of dynamic resources, say that you decide, I have 25 instances that are going to work, right? And you split up the work into 25, and then later you're like, you know what, I'm going to throw 30 at it. You're going to have 5 instances that can't do anything. Right. Or you're going to have an instance that grabs 2 pieces of work because it's done quickly, and it gets it before the first one gets the other work, and you have idle instances. So you always need more work than instances, because there's always going to be a case where the instance finishes, gets another piece of work, it needs something to do. And that's where we kind of had to experiment, and we really did have to see how fast we could get these things coming back and that kind of thing.
Every time I've seen this, it's ended up being a set of experiments. There's a variable here, which is sort of how big are these chunks of work, and you pretty much have to experiment with different sizes and see what the characteristics of that are. I'm going to throw in one more factor to think about in this all, which is how long it takes to complete the work.
Yep.
Because if you assign a chunk of work that's going to take an hour, and 58 minutes through, that instance keels over, and now somebody else has to pick up the message and start all over again. That's not a desirable quality. So you want to kind of minimize the amount of work you have to repeat when that happens, but you have to compare that to these other considerations about performance
Yeah.
and about these other things about how big those chunks are. So there's actually a lot to think about here. I think we should probably move on from this topic because there are a couple other things that we want to discuss. But the net of this is, as you're breaking up the work into pieces, you want to consider these different factors, experiment a bit, and come up with sort of what's the best allocation for your application.
Right.
Let's talk about now a slightly different problem, which if I'd drawn with some foresight, I could have put on here as sort of a pipeline. But imagine that you've broken up this work into a bunch of pieces. So we now have a bunch of little pieces of work. These are dots now, apparently. And now we have this task of assigning them to VMs. Like, how do we actually send these pieces of work to the VM? Or just generically, how do we distribute work? And there are a couple things that we want to think of in terms of distributing the work, and one of them is we want a couple properties, right? We want to know that somebody is going to do the work, right? So we need reliable message delivery, and we want to minimize how often people repeat pieces of work. So the queue is sort of the natural thing in Windows Azure to do this. So I would encourage people who are building systems like this to build it based on queues and queue messages. Because the queue says that basically when one of these VMs takes one of these work items off of the queue, it's actually just invisible for a period of time, so no one else is likely to see that message. But if this VM fails to actually finish the work on that queue item, somebody else will pick it up and do it. This comes in with another feature of queues, or sort of a characteristic of any sort of reliable message thing like this, which is that it's very easy to guarantee that somebody gets the message. It's nearly impossible to guarantee that exactly one person gets the message. And so the semantics with queues, as we've discussed on this show before, is that you have to be ready to get the same message more than once, which means if you're using that as a way to distribute your work, it's necessary that if you get the same piece of work multiple times and operate on the same work multiple times, you still have correct results at the end. Sometimes this is easy because sometimes it's, well, run number 345, here's the result. And if somebody else comes along and does the same one, he just overwrites that result. The math comes out the same either way, everybody's happy. But be careful if you're doing things like summing numbers, or if you're making some change based on the work that you don't want to have repeated. The word is idempotent, so each one of these things, the pieces of work that you put on the queue should be idempotent, which just means if you do it more than once, the result is the same. Anything else there in distributing work that I forgot to mention?
Yeah, when we did this for the Monte Carlo simulation, we had a slightly different problem. I mean, it goes along with what you first said, which is if you're doing 8 million runs, if you do the same work more than once, it turns out that that's not a big deal, because particular for the Monte Carlo simulation, that doesn't impact the overall result, which is you're looking at this huge number of runs. To do the work more than once a couple times is not going to be a big deal. Similarly, if you drop the work, if it doesn't get done, or the message failed to get sent over the service bus or something like that, again, not a big deal when you're doing 8 million runs. However, if it's the case where, as you're saying, you have to have a set number of runs, it has to be exactly correct, or maybe you're doing intermediary steps where there's a transformation in between, and as you're doing that transformation, something fails. You need to make sure that either the next time it gets picked up, you can do those transformations, or jump to the last thing that happened and pick up from there and just continue. But what you don't want to get is into a state where you pick it up and there were these intermediate transformations, and that causes an error because you were not expecting that to happen or to already be there. So that's the thing you have to look at. In this case, we didn't have to do that, luckily, right?
Yeah. Okay. So let's talk about actually one of the things that comes up with using the queue, which is visibility timeouts. I think this is a good time to talk about that. I don't know if I really have anything to whiteboard for this one actually, but we'll come back here in a second. But when using the queue, one of the things that you have to do is you have to say what the visibility timeout is. Is you take that message off, how long is it invisible before it reappears on the queue and someone else picks it up? And again, it's this trade-off between sort of extremes. I mean, one thing that you can imagine is it's just immediately available on the queue again,
Right.
and that would minimize the amount of time you have to wait if you failed and somebody else has to pick it up. It would take no time at all because it's right back there on the queue. But it would also mean that almost certainly multiple workers would pick up the same queue message, because until you actually deleted it, it would still be there. Everybody would pick it up. The other extreme is set it to 2 hours, which is currently the maximum on how long that invisibility timeout is. Set it to 2 hours, but really you only take 5 minutes to do it usually. You're not going to have the problem of someone else getting it before you're done, because even if you take twice as long as you usually do, you're well within the 2 hours you said. But if you fail, it's going to be 2 hours before anybody else sees that message. And assuming the run that you're doing isn't going to take nearly that long, that's sort of disastrous. It means that something that was going to take half an hour to complete is now taking hours and hours because
Right.
messages are having to reappear later and get picked up again. And so the ideal is if you could somehow gaze into a crystal ball, know exactly how long you're going to need this message, and set the visibility timeout like that. It's not quite the ideal, but let's hold it for now as the ideal. And Ryan actually had an interesting idea earlier about how you can, on the fly in the service, determine how you don't need a crystal ball because you're doing a lot of these pieces of work. And why don't you explain that?
Well, the gist of it is, right, we have a bunch of runs, usually in an HPC style application. You're doing lots and lots of runs.
Yep.
Otherwise, you wouldn't need to spread it across, right? So each instance hopefully doing more than one piece of work. What you can do is you can set the visibility timeout to the maximum, maybe for the first one, or to something that you think is much safer, like 10
Yep.
minutes or whatever it is. And then as you're doing the work, you start to calculate the actual time it took you to do the work within the role itself. So on the fly, you're starting to average the amount of time. Eventually, those numbers are going to coalesce with the more runs you do, and they're going to kind of come to a somewhat stable average, usually. And then what you do is you take that and maybe round up a minute or something like that and use that as the visibility timeout. So you have your code
Right.
auto-adjust the window it needs based on how much time it's taking them. And that's going to vary too, depending on what the work is, what size VM you deployed on,
Yep.
right? If you're doing work that assumes it's going to use the test parallel library and you only deployed a single core, it's going to take longer
Right.
than if you...
It's just different, right?
Yeah,
if
you're
you're
gonna
CPU
totally
bound, yeah, right.
It's going to be a totally different thing. So that's one way of doing it. The other is, manually tweaking it.
Right.
as
The
it
other one is
runs.
just, you can do that process. You can just kind of look at how log a bunch of things, which you should always be doing, and see how long it's taking, and next rev of your code, just sort of set that. Now, this is still not ideal. Remember, I said that this, this isn't actually the ideal thing. Because
So just ignore everything I just
yeah,
said.
just ignore all that.
Yeah.
No, because suppose you find out that this work always takes 45 minutes. So you set the visibility timeout to 45 minutes, you spend 1 minute working on it and then crash. Right? Now we have this 45-minute delay before anybody else picks it up.
Right.
And so it's not actually necessarily perfect to get it there. Now, a future feature of Windows Azure Queues is that you will be able to sort of renew your lease on the queue, and so extend the visibility timeout as you go, which means you could take it off the queue, set it to 2 minutes or whatever, sort of a reasonable minimum, and then as you see that the time is about to expire and you're not done, you can just renew it. You could just go, okay, actually make it 5 minutes, make it 10 minutes.
Yep.
This
me
lets
another
you
2
deal with a
minutes,
lot of, and the most likely thing is at the top of the loop or whatever, or you start a thread that every minute or so
It's a
renews
thread
the
called
thing.
"Thank you, sir. May I have another?"
Yeah, yes. And so that will let you deal with this. So that gives you the best of both worlds, because you've got the message for the duration of the work you're doing
Yep.
on it. But if you fail, it's quickly picked up by another worker. And those are really the two things that you're after. For now, since you can't extend that visibility timeout, you're in a bit of this trade-off, kind of pick the right thing. One recommendation I have is to try to make sure that all of the pieces of work take roughly the same amount of time, that they're all roughly the same size. If you don't do that, you're going to have a very hard time figuring out what the visibility timeout should be and doing this
Right.
in an efficient way. You're going to end up with a least common denominator sort of thing. So try to make sure they're all sort of consistent in size, and then pick that number that kind of fits there. This might influence how you decide to chunk up the work to begin with. So when you decide on the size of those work items, you might want to think through what's the implication if I'm using the queue to distribute the work. So maybe it's the last thing that we should talk
Exciting
about
the last
is aggregating those results and
Well,
sort of
first,
returning
before
back.
you go off there, one of the cool things that you had talked about is until we have that ability to auto renew, or I should say extend the lease, extend the visibility timeout, is you can work around it now. And you could do that by just a little bit of ingenuity involving leasing a blob simultaneously. So one of the patterns that you could use, and maybe I'll let you explain it, but it's a clever thing, so go ahead, explain it.
Okay, because it's clever, I'll explain.
Yeah.
I don't know what that means exactly, but yeah, the idea is paired with each queue message is a blob. And
0
you
bytes.
might actually end up having this anyway. You might actually have a queue message that just refers to a blob that has a whole bunch of work that's a lot of data or something. So very often you already have a blob that's associated with a queue. You might also have a blob that's associated with the output, which is what we're going to talk about next, how you collect these results again. If so, you can reuse that blob for this purpose. But if not, as Ryan said, you just create a 0-byte blob that goes with the queue message. And you dequeue the queue message with a reasonably short visibility timeout, and you immediately try to acquire a lease on the blob because we now have the capability of leasing blobs for a minute at a time. So try to acquire the lease on the blob. If you get it, great. Keep renewing that lease as you work and keep going and don't worry about it. If someone else gets that message, they'll try to